So in this video, we're going to begin learning about the shapes of sampling distributions. So here we have the title, The Shape of the Sampling Distribution of X bar if X is normal. If a random variable X is normally distributed, then the sampling distribution of the sample mean X bar is normally distributed. Translation: if the population from which our sample's being drawn is a normal distribution, then our sampling distribution of X bar is going to be normally distributed as well. Plus, what we've learned previously is that the mean of the X bar distribution equals the mean of the population, and the standard deviation of the X bar distribution equals the standard deviation of the population divided by the square root of the sample size. So we have a visual here to kind of help us see the difference. Okay, again, as I said in the previous video, you need to be clear that we're talking about two different distributions. So the blue curve here is representing the population. So this population has a mean of mu and a standard deviation of sigma. If we take a sample of size n from that population, then the mean of the sampling distribution, which is represented by this red curve, is going to be mu sub X bar. So again, notice that the mean of the population and the mean of the X bar distribution are the same. So both of those distributions are centered at the same place. But the standard deviation of the population, sigma, the standard deviation of the X bar distribution is going to be this sigma divided by the square root of the sample size. And so that's going to give us a smaller standard deviation, which means we're going to have a skinnier looking, taller normal distribution. And again, the significance of this theorem is that if we know the population's normal, then this sampling distribution is going to be normal also. So let's look at an example of this. The upper leg length of 20 to 29-year-old males is normally distributed with a mean length of 43.7 centimeters and a standard deviation of 4.2 centimeters. What is the probability that a randomly selected 20 to 29-year-old male has an upper leg length that is less than 40 centimeters? A random sample of 9 males who are 20 to 29 years old is obtained. What is the probability that the mean upper leg length is less than 40 centimeters? C. What is the probability that a random sample of 12 males who are 20 to 29 years old results in a mean upper leg length that is less than 40 centimeters? What effect does increasing the sample size have on the probability? Provide an explanation for this result. And E. A random sample of 15 males who are 20 to 29 years old results in a mean upper leg length of 46 centimeters. Do you find this result unusual, and why? So what we're told in the setup of this problem is that the upper leg length of 20 to 29-year-old males is normally distributed. In other words, the population is normally distributed. The mean is 43.7 centimeters and the standard deviation is 4.2 centimeters. So this is the mean of the population. This is the standard deviation of the population. In part A, we're asked what is the probability that a randomly selected 20 to 29-year-old has an upper leg length. So we're picking one person. And the question is, what's the probability that one person will have a mean upper leg length of less than 40 centimeters? Well, how is that different from problems B and C? Well, in problem B, we're not picking one person, we're picking 9. And the question is, what is the probability that the mean of the 9 will be less than 40 centimeters? And then in part C, we're not picking 1, we're not picking 9, we're picking 12. And the question is, what's the probability that the mean of the 12 will be less than 40 centimeters? And so then we'll continue with parts D and E. But let's look at parts A, B, and C on a separate sheet. Again, we're told that the population is normal. And what we're talking about here is the population of the upper leg lengths of 20 to 29-year-olds. We're also told that the mean of the population is 43.7 centimeters, and the standard deviation is 4.2 centimeters. Okay? So in part A, we're asked if we pick one guy, what's the probability that his upper leg length is less than 40 centimeters? So we're being asked, what's the probability that X is less than 40 centimeters? Now this problem could have been a problem right out of the previous chapter. It's exactly the same kind of problem we just did in the previous chapter. So to figure out what this probability is, I know I have a normal distribution. The upper leg length is X. The mean is 43.7 centimeters. And so the probability of finding a guy that has a leg length of less than 40 centimeters would be this area here. And so we've learned several different ways that we could figure out what this probability is. We could do it by hand using a normal table. We could use a normal CDF command on the calculator, or we could use StatCrunch. Now I'm not going to do it all three ways. I'm going to just use my TI calculator in order to figure this out. So to figure this out, I'm going to use the command normal CDF, and my lower bound is, we don't really have a lower bound, so that's going to be a big negative number, so negative 10 to the 99. My upper bound is 40. The mean is 43.7, and the standard deviation is 4.2. So this is going to be my normal CDF command. So I'm going to pull my calculator in here. So I'm going to go to distributions and normal CDF. My lower limit is a big negative number, negative 10 to the 99. My upper limit is 40. The mean is 43.7, and the standard deviation is 4.2. And so I get a probability of 0.1892 if I round to 4 places. So this probability is 0.1892. So in part B, to revisit, we're picking a random sample of 9 males. And the question is, what is the probability that the mean of these 9 males will be less than 40 centimeters? So how is that different? Well, it's different because we're talking about a different probability distribution. So now we're talking about a sampling distribution. And we know that the sample size is 9. Well, the fact that the population's normal tells me that this sampling distribution's normal also. So I know this sampling distribution is normal. And again, I know that it's normal because the population's normal. The mean of this sampling distribution of X bar is going to equal 43.7 centimeters, which is the same as the mean of the population. We know that from our previous theorem. The standard deviation of this X bar distribution is going to equal the standard deviation of the population divided by the square root of the sample size, which in this case is 9. Now the square root of 9 is 3, and 4.2 divided by 3 is going to be 1.4. So this is 1.4 centimeters. It's centimeters because it's 4.2 centimeters divided by the square root of 9, so the unit stays centimeters. So I have this sampling distribution of X bar, and it's going to be normal. Now it's actually going to be taller and skinnier than the population standard deviation, but the center is going to still be 43.7 because that's the mean of the X bar distribution. So we're being asked, what is the probability that the mean is going to be less than 40 centimeters? Okay, so notice the difference in my notation. Here we were picking one guy, so I said, what's the probability that X is less than 40, like we used in the previous chapter? Here, though, it's not one guy, it's the mean of 9 guys. So I'm asked, what's the probability that X bar is less than 40? Now, I work it basically the same way. That's still going to be this area right here. But, again, my mean's 43.7 because it's going to be the same as the population, but my standard deviation's different. Okay? So if I again use the calculator, I'm going to use the normal CDF command. But again, I could do this by hand. I could use StatCrunch. So you're welcome to do that. So again, I have no lower bound. It's going to be a big negative number, which is negative 10 to the 99. My upper bound is 40. My mean is 43.7. But this time, my standard deviation is 1.4, not 4.2. So if I pull my calculator back in, I'm going to do distribution, normal CDF. I've got my big negative number to 40 with 43.7. I just need to change the standard deviation to 1.4. And so I get 0.0041 for that probability. So if I pick one guy, the probability that that one guy has a upper leg length of less than 40 centimeters is 0.1892. But if I select 9 guys, the probability that the mean of those 9 guys is less than 40 centimeters is 0.0041, so much less likely. Let's continue with part C on another sheet. So in part C, we're going to take a sample of 12 individuals. So again, we're going to be dealing with the sampling distribution. But this time, our sampling distribution is coming from a sample of size 12. Okay? Now again, because we know the population's normal, we know that this sampling distribution is going to be normal as well. Again, I know it's normal because the population's normal, and our theorem told us then that that had to be true. So the mean of this sampling distribution is going to be 43.7 centimeters, the same as the mean of the population. But the standard deviation of this sampling distribution is going to be the standard deviation of the population, 4.2, divided by the square root of the sample size, which in this case is 12. So if I take 4.2 and divide by the square root of 12, that is about 1.2124. So this is about 1.2124, and actually I'm going to go a couple of other places, 36. 1.212436. We always want to carry it out several places because rounding can cause us error. Now, so in this case, I have this sampling distribution of X bar. So I have an X bar distribution. Notice my notation here. The mean is 43.7. And this sampling distribution would be even taller and skinnier than the sampling distribution when we had n equals 9 because we have a smaller standard deviation. So the smaller standard deviation makes us even taller and skinnier. Now, again, we're looking for what's the probability that the X bar for these 12 guys is going to be less than 40 centimeters. And we can use either the calculator or StatCrunch, or we can do it by hand to figure out this probability. Regardless, here's 40 centimeters, so we're looking for this area to the left. So if I use my calculator, the command will be normal CDF. Again, my lower bound is going to be a big negative number. My upper bound's 40. My mean is 43.7, but this time my standard deviation is 1.212436 approximately. So if I pull my calculator back in, go to distribution, normal CDF, big negative number to 40, 43.7, but my standard deviation now is 1.212436. And so I get a probability of 0.0011. So pulling back in my problem, we've answered part A, we've answered part B, we've answered part C. And so question D, what effect does increasing the sample size have on the probability? Well, if I pull back in my results from parts A and B, when we selected one individual, the probability of being less than 40 was 0.1892. When we selected 9, the probability that the average or the mean of those 9 is less than 40 centimeters is 0.0041. When we picked 12 individuals, the probability that the mean of those 12 individuals was less than 40 centimeters is 0.0011. So as our sample size increases, the probability of being less than 40 decreases. So the answer to part D, the probability decreases. Now, does it make sense why the probability is decreasing? Remember the law of large numbers. As the sample size increases, then the x bar is going to approach the true value of the mean. So as our sample size goes up from 1, which really isn't a sample, to 9 to 12, it's going to be harder and harder and harder for x bar to vary from 43.7. So it's harder when the sample size is bigger for the average x bar to be less than 40. It's getting harder and harder as the sample size goes up because it's harder for the x bar to vary from the true mean. Now let's conclude this by looking at part E. So pulling back in part E, a random sample of 15 males who are 20 to 29 years old results in a mean upper leg length of 46 centimeters. Do you find this result unusual? Well, so looking at part E, would it be unusual means that we need to find the probability of that occurring. So first of all, notice we have in this problem again, we have a sample of 15. So once again, we have a different sampling distribution. So we have a sampling distribution, but our sample size is 15. Now again, we're going to know our sampling distribution is going to be normal. The mean of this new sampling distribution is still going to be 43.7 centimeters, the same as the population. The standard deviation of this sampling distribution, though, is going to be 4.2, the standard deviation of the population, divided by the square root of 15, our sample size. So if I pull in my calculator, 4.2 divided by the square root of 15, that is 1.084435. So this is about 1.084435. Again, I'm carrying that out several places so that rounding doesn't present us a problem. And so our question was, if we got an upper leg length of 46 centimeters, would we find this result to be unusual? Well, if we find the probability of our upper leg length of being 46 centimeters or bigger, we can see if that is less than 5%. If it's less than 5%, then that would be unusual. So I have my x bar distribution. 43.7 centimeters is here, so 46 is going to be over here. I'm looking for this probability and seeing if that's less than 5%. If it's less than 5%, then it's unusual. So again, I can do this either by hand, with StatCrunch, or with the calculator. I'm going to use the calculator. So we have normal CDF. This time we have a left bound of 46. We don't have a right bound, so I'm going to use a big positive number. The mean is 43.7, and the standard deviation is 1.084435. So if I pull my calculator in, I'm going to second and distribution, normal CDF. So this time my left bound is 46, My right bound is a big positive number. My mean is 43.7. My standard deviation is 1.084435. And so that gives me a probability of 0.0170 if I round to 4 places. So there's my probability. That is less than 5%, so the answer would be yes, this would be unusual. So in this example, we have looked at sampling distributions where we knew the mean and the standard deviation of the population, and we knew that the population was normal.